Good afternoon. So I'm so happy to be here to present our recent work on dynamic regress bound for TOA-based tracking problem. This is a work that I worked with my supervisor, Professor Anthony So, and it will be appear in the proceedings of CDC, the coming CDC in December. So let's start. We'll begin with the introduction. So we'll talk about the background of the TOA tracking problem and why we'd like to use the online approach. And then to develop the dynamic regress bound, we will talk about the local strong convexity of the static localization problem. And then we'll talk about the dynamic regress bound and we'll provide some simulation results to support our findings. And at the end, we'll give a conclusion. So as you know, localization is everywhere. If you want to locate yourself, you can always use Google Map. And sometimes we don't want to just locate yourself. We'd like to keep track on the trajectory. For example, in a manned aerial vehicle, so we'd like to see whether the trajectory is correct or not, and would like to direct the car to the correct places. And similarly for robotics and some surveillance system, we'd like to keep track of the location of some items or robots. So there are quite a number of localization methods like TOA, time of arrival, measurements, TDOA, time difference of arrival, RSS, received signal strength, AOA, angle of arrival. So as you know, RSS and may give a lower accuracy, and AOA needs a lot of anchors or nodes. So in our talk, we'll talk about TOA measurements. And this is a main measurements that is often used in IRUWB technology. Another line of work is visual tracking, and so we track some items via a series of images. But well, this will not be the focus of today. TOA measurements, it's given by the signal propagation time between the anchors and the source, the target that would like to find its location. Using the signal propagation time and we multiply by the speed of light, then we can get the distance between the anchors and the target. So we may, of course, we may use TOA to do static localization problems. So we can compute the problem all over again. But for tracking problem, we don't want to just simply keep doing the whole computation again, because it's kind of wasting the previous information, because we assume that in a tracking problem, the location would not be far away from each other between each time steps. So as you can see, in traditional approach, common filter or the online approach that we're going to introduce later, both uses previous information to update the new estimate. So in a common filter, we have the location is evolved by a linear model described here. XT is a state vector, consider the location, also the velocity. And phi is the state transition matrix. And delta t is the time difference between each time step. And UT is the dynamic model that act on the velocity. So as you can see, 1, 2, 3, 4, 5 are the procedures in common filter. The main point is, as you can see, ST here represent the covariance matrix. So we keep updating the estimate of the location and the velocity, also the covariance, so that using the common gain, we can minimize the residual error. Okay, so this is a traditional approach that has been studied in a lot of literature in tracking problem. But today our focus would be on a recent approach, the online tracking. So in an online framework, each time we have a loss function that we like to minimize it. So let's call it ft. But at each ft, we don't know, at each time step t, we don't know ft. So we have to use the previous information to approximately minimizes ft. So in our case, say we want to estimate the target location at time t plus 1, but we don't know ft plus 1. Then we have to use the information from previously that we got, say f1 up to ft. So why we want to use this approach? Because this is simple, and this is simple and fast. As you know, it has been studied quite a lot in machine learning community and also the control community. And also from a theoretical point of view, we have the notion of regrets that's quite well developed, and we can use this to analyze the performance of our algorithm. So now let's talk about the formulation of our problem. We have from t equals 1 up to big T, the time of horizon. Each time the source, or we say the target, is unknown, the location of the target is unknown, and we denote this as xt star. But each time the anchors are fixed. So, and we know the position, and we call this AI. And there are a total of m anchors here. So each online TOA measurements are given by the distance between the true source location and the anchors plus some noise. Okay. But again, at a time t, we don't know these online TOA, these RIT measurements. We can only have the information of RIT minus 1. Okay. So, and this noise is IID, that is an independent, identically distributed Gaussian noise with mean 0 and variance sigma squared. And this Gaussian noise for each time t, it is independent with each other. Okay. And for the loss function, we define the loss function as the summation of square difference between the distance x minus AI and RIT, the TOA measurements. So this is the reason why we set this as a loss function, because in static localization, this is actually the maximum likelihood function. So we often use this kind of this format of function to estimate the location of some target. So in online framework, to evaluate an algorithm, we use the notion of regret, as I've mentioned. This is defined as the summation of ftxt, that's the loss function value of our estimate, minus the loss function value of the minimizer. So in our case, the minimizer would be the ML estimate. And xt hat is the minimizer of ft. So the regret rate captures the accumulative losses of the deviation of our estimate and the minimizer. And as you can imagine, as you can expect, ftxt minus ft hat would be non-negative. So the regret, if we plot a graph with different t, it will accumulate and grows. Okay. So, however, the loss function in our case is non-convex and actually non-smooth at some point when x coincides with the anchor. So general literature cannot, on online optimization cannot apply to our to the TOA setting. So now let's review some of the related work. In 2016, we have a work on the sequence of strongly convex losses with the method using online gradient descent. We call it OGD, and the regret is given by is in terms of the path variations. And then later, Zhang and his co-authors improve the loss function so that it can cover functions with quadratic growth, or they say semi-strongly convex functions, and they give a similar bound. And later in Lesage Landry's work, they prove for non-convex function using online Newton method, they can give us a similar regret bound here. So in our work, we would like to exploit the structure of this loss function. And even though it is non-convex, we want to show that using online gradient descent, we have some similar regret bound here. So this is the roadmap of today's talk. First, we want to show that each FT is locally strongly convex. This is a very interesting result and can have some implication in static localization, and we will talk about it along the talk. And then given that it is locally strongly convex, and as long as xt is in the strong convexity region of ft plus 1, then we can consider it like a strongly convex sequence of strongly convex functions, and then we can exploit the existing results to establish the regret bound. So let's begin with local strong convexity results on the static localization. So from now on, for the static localization, we will remove all the t because now we don't need the time t. And then actually the notations are similar. We have Ri that measures the TOA measurements. And then Wi is IID Gaussian noise. And then here the maximum likelihood function is given by this form. That is that looks really similar to our loss functions for different time t. Although TOA measurement, based localization is quite a well-studied topic, a lot of algorithms have been proposed on this kind of localization problem. However, there are actually very few theoretical results on this. A popular one is Beck's work, and they show that the gradient descent would converge to a stationary point of the ML function of TOA-based localization, and they prove some sufficient descent also there. And later in our work with Hui Kang, also a member in our group, but now he's in Imperial. And then we developed the local strong convexity of the ML function in TDOA setting. Using the local strong convexity, we not only know the geometry around the near the ML estimate. Also, if we have some proper initialization, so it's near the MLE, then we can have some good convergence rate that converge to the MLE. So we will also talk about this in our work, because we actually can find also some similar structure in the ML function of TOA. So before we talk about the local strong convexity, we start with the estimation error, which will be quite crucial in our development in local strong convexity. So we have the unknown true source location x star here, and we like to estimate x star via an optimal solution in the ML function of the TOA localization, and we denote this as x hat. To be careful, x hat may not be the same as x star, because we just use some noisy measurements to estimate the location, and you know the ML function of TOA localization is actually NPR. So we use this to estimate it, and we estimate, we say that the estimate x hat is very close to the true source location x star. Okay, so here in proposition 1, we develop that the distance between x hat and x star is upper bounded by the quantity here. As you remember, m is the number of anchors, sigma is the standard deviation of our measurement noise, and as you can see, the ML estimate x hat and the true source location x star will be close to each other when the noise power is small. So and K1 and K2 are some constants that are determined by the position of the anchors and the ground truth and the true location. Here we only have one assumption here that's imposed on the noise. W is the noise, and we assume that the norm of the noise is upper bounded by some constant times the square root m times sigma. So this assumption actually is satisfied with high probability by concentration property of Gaussian noise. So as long as this assumption is satisfied, this will be held deterministically. Okay, but this assumption can be held with high probability. Okay, so now let's sketch the proof here. Recall that our TOA measurements Ri is, I have missed a star here. So the true location x is the true location of our target, and the anchors, the distance is very similar to, can be approximated by the TOA measurements Ri here. And of course, we can expand this in this way. And then, as you can see, each term x star, we have the squared term here. But for, say, AI plus 1, using AI plus 1, we can cancel each other by subtracting the two equations. So we have a system of equations here that, and we would like to minimize ax minus b here. So as you can imagine, we minus the ith equation minus the I plus 1 equation minus the ith equation would give us such kind of system. So this system is overdetermined, right? So, but we can easily get the least squares using this formula. Okay. This is a key step. We say this least squares, and for 0.4 and 0.5, we will also use this system. So as you can see, our trick is to compare the terms. We use here X star. Of course, we can plug in and we get our I star here. And of course, X star would be the minimizer of the minimizer of AX minus B star, and B star is defined by this factor, but replace the Ri by Ri star. Okay, and then of course, if we consider B minus B star, so simply there are only Ri squared minus I star squared there. So again, we impose our noise assumption, then we can get this upper bound on the distance between the least squares solution and the ground truth. And similarly, we can also do the same on x hat. So if we plug in x hat here, and then we have our I hat here, which is defined by the distance between the ML estimate and the ith anchors. And then again, we have A transpose A inverse A transpose B minus B hat. So here B hat, we replace our I here as our I hat. And then B minus B hat, again, we have some terms like our I squared minus our I hat squared. And again, we can use the noise assumption and we upper bound this by a similar form, some constant times square root m sigma plus some constant time m sigma squared. And then after we have established these two inequalities, then we can use the triangle inequality, and then we can establish the distance, the upper bound of the distance between x hat and x star. So this is how our proof is, how we prove the proposition. So having this estimation error, we can now prove the local strong convexity. So we need the noise assumption, and we do not want the true location to be too close to the anchors because of some differentiability issues. And then we have at the ML estimate, the Hessian is positive definite. That is, we have some local strong convexity result at the ML estimate whenever the noise is small enough. Okay. So the noise here is determined by this formula. Okay. This formula, as you can see here, K1 and K2 are some constants in proposition 1. M is the number of anchors, N and this big lambda are also some constants determined by the positions of the anchors and the target. And then C0 is comes from the noise assumption, and also and also we have this term, the minimum eigenvalue of the summation of the unit vectors of the true location from the anchor's position, and this involves the geometry of the whole set configuration of the anchors and the and our target. So as you can see, the W here, as we want this to be bigger, so we can have some more flexibility on the noise level. And here W is controlled by, so we don't want all the the vectors the true location of the source from the anchor to be pointing to the similar direction. We want it to be spreading out. Okay. So in this theorem, we also give the local strong the strong convexity region. So here we for the vectors near the MLE, we have the Hessian also being PD, as long as the norm of epsilon is not too big, and is given by the minimum of delta and thus quantity. Delta again is the distance between the anchors and the target, and we don't want this to be too close for differentiability issues. And then W again, we have mentioned the geometry of anchors and the source. And then actually the quantities, this depends on similar factors from what we have just talked about. This strong convexity region is particularly important in our analysis later for the dynamic regret bound, because we want the, as you remember, we want the estimate to always to be in the local strong convexity region, so that we can use some existing results and essentially performing online optimization on sequence of strongly convex functions, and so that we can exploit the existing results. Okay, so it turns out that to prove the local strong convexity, also the strong convexity region, we can use one proof to prove both things. So here now let's sketch the proof. Because we want to prove strong convexity, right? Local strong convexity. So of course we first compute out the Hessian. So the Hessian is given by the summation of this whole thing, some quantity times the from x from some anchors and its outer product, and some quantity times the identity matrix. And then because we want to prove the also for the vectors near the MLE to be PD, so we simply plug in x hat plus epsilon to this Hessian formula. Okay, so we plug this in, and but we have no idea on x hat plus epsilon minus AI. So, but we have some, we can put the x star minus AI as some constant vectors, right? So we put this and minus x star minus AI, this outer product of the unit norm, and then we plus this. So this is the difference of the outer products of some unit vectors, UU transpose minus VV transpose, and of course we can use some lemmas to bound this too, and then this will be left as some constants. Okay, so the first term we can bound this, and then for the second term, actually we can simply pass the denominator, and then we have such kind of form. I recall this is the noisy TOA measurements. So this is the true measurement and noiseless measurements plus some noise here. So WI, we can again use the noise assumption to bound it. And then we can use some triangle inequality so that we have some terms like x hat minus x star. So as shown here. Okay. So and using this, and then at the end we can get this minimum eigenvalue is lower bounded by this, and we want this to be positive. So again, we force the right-hand side to be positive, and rearranging the terms, we have the norm of epsilon is upper bounded by this quantity. So we now have proved the local strong convexity region, but it doesn't make sense if this quantity is negative, right? So to prove the local strong convexity, we have to ensure that this quantity is non-negative or positive, okay? So putting this as positive, and as you can see, there's a squared term here, and that's why we have this quadratic form here, okay? And that's why we can get this theorem proved. Okay, so as I have mentioned, with the local strong convexity results, we can have some implications even for the static localization problem. As we remember, we have the linear convergence in gradient descent for strongly convex functions, right? So this time, if we have some proper initialization near within the local strong convexity region, then we also have the linear convergence of the gradient descent converging to an optimal solution X hat. Okay, so here I have shown the two examples to show that we really have the linear convergence here. So in this numerical example, we have the anchors to be distributed uniformly on a circle with radius 10. So it's a big circle, but the source is randomly generated within a small square inside. And even we set the noise to be 0.1, sigma equals 0.1, and we run 1000 Monte Carlo runs, we still have this beautiful linear curve here. Okay. So with the local strong convexity, we now can move on to our dynamic regress bound. So we have now already proved the local strong convexity, and of course we'll use it. And then, before that, we recall the formulation. Simply, we just put all the t back. So the t here represent the time, and at different time t, we have different source location or target location, and we have different noise that is independent with each other, and different TOA measurements, and the loss function is given like this. Okay. So in our work, we use the algorithm online gradient descent, as I've mentioned. So it works like this. To estimate the location at time t+1, we use the location at time t, and then we run one iteration of gradient descent on ft with step size eta t. Okay. So of course as we recall, we have some results on online optimization on sequence of strongly convex functions. So we can, as long as we ensure that xt lies in the strong convexity region of ft+1, we are essentially performing online optimization of sequence of strongly convex losses. So, but how to establish this xt lies in the strong convexity region? So we have to do it now. So we want this to be true, and to ensure this happen, we have xt. We would like xt to be close to the minimizer of ft+1, right? So we bound the distance of between xt and xt plus 1 hat. And then we can write this using triangle inequality like as the right-hand side. So we simply xt minus xt hat, and then xt hat minus xt plus 1, and then xt plus 1 minus xt plus 1 hat. Okay. So as you can see, this term and this term is actually looking really similar to each other. So we can, as long as we can prove that xt is always close to the minimizer of xt hat, then this can be done. And for this term, xt plus 1 minus xt hat, recall that xt plus 1 is is performing one iteration of gradient descent on ft, right? And xt hat is the minimizer of ft. So it's essentially doing the offline gradient descent, right? So and here we first assume that ft is mu strongly convex over the local strong convexity region, and then the gradient is L Lipschitz continuous, and the norm of the gradient is upper bounded by some g, and over the local strong convexity region. So these are some standard assumptions in online optimization literature. And of course, these three will hold because first, this is the characterization of what we've just proved. And then this, as you can see, the ball here is compact. This means the ball that is centered at xt hat with radius epsilon t. And this is compact. Also, we have the gradient and Hessian to be continuous in this ball. So we can, just that we have to see what mu, what L, what G is, but certainly these three can be satisfied with some mu, some L, and some G, okay? And then how do we bound this one? Recall that the gradient descent is converging linearly for strongly convex function. So we have this, this fact that here k is some iteration number, so it is xt minus we can simply plug this in xt minus xt hat xt plus 1 minus xt hat squared is upper bounded by some constant times xt minus xt hat squared. Okay, and this constant will depends on either the step size, mu, the strong convexity parameter, L, and the Lipschitz gradient parameter, and later in our proof we'll denote this as rho. Okay, you'll see it later. Okay, then this term can be also written in similar form like this, and then as long as we can prove that xt is really close to xt hat, then we are essentially done, right? So in this, in the common proposition 2, we are going to prove this, okay? So suppose x0, so suppose we know the initial location of the source, the target, and then we use this as our initialization, and assume that the sigma, the noise power, and the path variation Vt are sufficiently small, then we have xt lies in a strong convexity region. Oh, this should be ft hat, I guess. And this, and also we have xt minus xt hat is upper bounded by some quantity. And as you can see, this upper bound depends on the number of anchors, m. Here, sigma, the noise power, and also V, also a V here, that is the path variation. So as long as the noise power is small, the path variation is small, this can be upper bounded by some small quantity, and as long as this is xt is really close to xt hat, and then we have xt lies in a strong convexity region of ft hat. Okay, so this actually can be proved by mathematical induction. So for the induction base, we define f0 because at time 0 we actually don't have any loss function, but we define this as the summation of the distance between the x and the anchor, ith anchor, minus the true distance between the initial location and the anchors, and we have a squared here. Then x1 minus x1 hat can be upper bounded by x1 minus x0 hat plus x0 hat minus x1 hat. And again, using triangle inequality, we have this holds. As you can see, x0 hat is exactly equal to x0. And then here, x0 hat is exactly equals to the true location x0 star. And then we can then we have recall that f0 is given like this. Then x1 will be actually the same as x0 because already we have the exact location, and then the gradient would also be 0. So this term is 0, and then this term can be upper bounded by path variation, and then this term can be upper bounded by the estimation error, which we have talked about it in the in proposition 1. Okay, then for the induction step, similarly, we do this for xt plus 1 minus xt plus 1 hat, and we can expand this like this, xt plus 1 minus xt hat, and then plus xt hat minus xt star, and plus xt star minus xt plus 1 star, and then plus xt plus 1 star minus xt plus 1 hat. So here, this can be upper bounded again, like using using the facts of linear convergence of gradient descent, and we have a row here, xt hat minus xt star, also xt plus 1 star minus xt plus 1 hat, we can upper bound it using estimation error, and then this can be upper bounded by the path variation v, and then at this step, we can complete the proof using the induction hypothesis. Okay, now finally, let's come to the another main result in our work. That's the dynamic regret bound. Again, we assume that we know the initial location, and we set this as our initialization, and assume the noise power and the path variation are sufficiently small. Then we have the regret bound upper bounded by this quantity. As you can see, this is the first term here. G, M1, M2, M3 are some constants. As you can see, this is in terms of the path variation. This is in terms of the noise power times some t, so it grows linearly, and plus some constant here. Okay, and here, if we look carefully, M1 is depends on, again, K1, K2, and the number of anchors, the noise power, and the V0 is the initial move, and M2 depends on M1 and also the number of anchors and the noise power. And nu here is given by this and depends on the strong convexity parameter, also the step size. Okay. So here are some interpretation on the dynamic regret bound. As you can see, as for in online optimization literature, usually we have the path variation growing sublinearly. So we have the path variation as t grows. The distance between each move is getting smaller and smaller. Okay, and then as you can see, this term is growing linearly. Okay, so even for sigma to be very, very small at the beginning, very, very small, and this term dominates at the beginning, but eventually we can expect that the noise term actually dominates, and eventually we have the linear growth. Okay, and actually in our experiments we can also see such kind of behavior, and we'll show later. And recall that regret bound is some evaluation of on the online algorithm, right? So when the path variation here is very small, and then the sigma here, the noise power is very small, then we have the regret bound to be upper bounded by some small quantity, and that means online gradient descent performs well in such scenario. And it actually makes sense because when the path variation and noise power are small, then of course we can estimate better, right? And as you can see, there are we have a quite strong assumption on the path variation and noise power, because we want to keep this in the local strong convexity region, right? However, in our experiments, the result is actually quite robust against large path variations and noise power. We haven't figured out why, and probably this can be studied in the future and see whether we can lose our assumption a bit. Okay, so now let's do the sketch of the proof. So actually we have developed quite, we have already quite well prepared. So we simply plug in all the results and we can get the dynamic regret bound. But I just simply recall this, okay? And describe the flow again. So we first apply proposition 1 and theorem 1 to obtain local strong convexity. And then we call that xt. So this is xt, not xt plus 1. Xt lies in the strong convexity region at t plus 1, because with high probability, and the assumption that the path variation and the noise powers are small enough, because we have this inequality. We can upper bound this using the noise power and also the path variation. And then as long as xt lies in the strong convexity region at t plus 1, then we can invoke the corollary in Mokhtari's paper, and we get the regret bound. We can, yeah, and that's why we get this regret bound holds. Okay. So now let's move on to the numerical results. We first set the anchors like this. So this is also the setting in Leslie Landry's paper, and they put the sense anchors in these 3 positions, and the initial location of the target is 2, 1. So it's not close to the anchors, and this is also good to our setting, because we want to avoid the differentiability issues. If this is too close, maybe it cannot be differentiable. So this 2, 1 is far away from the anchors. We set the move like this. dt is given by this. bt is the Bernoulli variable, and 1 is the all ones vector. And as you can imagine, this move would be rather going forward or going backward. Okay, so but each move would be getting smaller and smaller as t grows, because we have this over square root 2t. Okay, and then again, we know the initial location, so we can set this as our initialization, and our step size would be 1 over square root t. And then we run pretty lots of, we use a rather large time of horizon here. So we use big T equals 10,000, so that we can see the behavior of the regret rate. And we run 1,000 Monte Carlo simulations. And here, when the noise power is rather small compared with the move dt here, and we can see that this is growing sublinearly at the beginning, and then later it grows linearly. So it illustrates our theoretical findings. And when sigma is large, then we have simply one linear curve for the regret rate. So it actually also matches with our theoretical findings. So another example would be, so now let's change the trajectory. We don't generate the trajectory either moving forward or backward. We simply draw the move from a square using following uniform distribution. And again, we want each move to be, we want the move to get smaller and smaller as t grows. So we we divide this by square root t. And again, a similar behavior can be observed. As you can see here, it grows sublinearly and then eventually grows linearly. And for when the noise is larger, then we have this kind of linear curve. Okay, so another one is what I've just, another example is what I've just mentioned. So how about when we set the path variation to be large and then the noise power also large, then maybe it doesn't satisfy our assumption for the local strong convexity. But we actually can observe a similar behavior here. So here the move is actually times 100 compared with the example, the first example, and also the noise, we also put this as 0.01, which is much larger compared with the first example. But still, we can observe that it grows sublinearly at the beginning and then linearly eventually. And similarly, when sigma equals 0.1, we have such linear growing behavior for the regret rate. Just that the y-axis, as you can see, it's up to 18 and is up to 200, so it's much bigger than the first example. Okay, so now let's conclude the talk. We have proved the dynamic regress bound. We first established the local strong convexity for each loss function, the ML function at each time step. And then we have showed the estimation error, the local strong convexity, and as a side product, we have showed the linear convergence of gradient descent in static localization problem. And then using this local strong convexity result, we want to establish the dynamic regress bound, but we have to ensure that each xt lies in a strong convexity region of ft and ft plus 1. So we have show this in proposition 2, and then eventually grouping, collecting all the materials we have developed, we can establish the non-trivial dynamic regress bound. So this is the end of the talk. Thank you.
Thanks, Mandy. This was great. I just put the link to the ONM paper that you referred as well. And I just realized there is no one who will give that presentation, so I might do it sometime in November. Anyways, we have time for one quick question. Daniel.
Hey, Mandy. Thanks. It was a really good talk. So I've got a question about proposition 1. Could you go back to it?
Proposition 1. Let me see. Oops. Here?
Yeah. So imagine there's just one anchor and you have no noise.
I don't think we can estimate the location using one anchors. At least we have to use 3 anchors in 2D.
All right. Okay, that was my question. Because I think there's a counterexample if you just have one anchor.
Yeah. So you can see from this diagram. So if we want to locate the target and we have a TOA measurement here, we can simply only draw one circle, and it can be located anywhere on the circle. So we have to use at least 3 anchors to locate one target location.
Sure, cool. And sorry, one more quick question.
Yeah, of course.
Your assumption on the noise, which you said was satisfied with high probability, do you have to assume Gaussian noise? Because eventually, as you keep going, even though it will be satisfied with high probability, eventually it will be violated. So how do you deal with that?
Actually, in our setting, we assume Gaussian noise, and that's why we have the ML function, because we ML function here, because we assume this is Gaussian noise. Using other noise, this may not be the ML function for our problem. And then for this one, if we for this one, we do not even for non-Gaussian noise, as long as this is satisfied, then this proof will go through.
Mm-hmm. But eventually, as the length of the trajectory grows, it will be violated at some point. So does that mean you lose your tracking performance eventually?
If this is not Gaussian noise?
Well, with Gaussian noise, like eventually it will violate the bound, right?
I don't think so. This could be still satisfied with high probability.
But you will get at least one time step where it won't. Like as you set t to infinity, even if it's only a 5% chance that, or a 0.5% chance that it violates, eventually it will violate at some point.
Yeah, I see your point. So this is kind of a restriction in our proof, because we really need this this upper bound on the noise. Otherwise, this may violate, and we don't have this upper bound, this estimation error.
Yeah, cool. So it will only violate at maybe 1 or 2, points. Does that mean you can still recover, or maybe you need to do more work for that?
In our proof, this doesn't go through, but in our experiment, it seems to be go through.
Yeah, cool.
Yeah.
Thanks. Yeah, that's all from me.
Yeah.
Thank you. Thank you for your question.
Thank you very much, Mandy. We are out of time, so I ask anyone who wants to ask more questions, contact Mandy directly, and I'm sure there are more interesting questions there. I have a bunch of questions that I will email you. Thanks a lot.
Thank you.
Cheers. Thank you.